Good morning student. In the previous lecture we saw the data flow modeling. Now in this lecture we will see the examples which are related to a data flow modeling. So first is implementation of 2:4 decoder. Now in this example we have to design a 2:4 decoder by using data flow modeling. So first of all, what is 2:4 decoder? So 2 into 4, this is the block diagram of 2 into 4 decoder. So 2 into 4, that means this device or this circuit has 2 inputs and 4 outputs. 2 input and 4 outputs. Okay. So the truth table is 2 input IN0, IN1 and 4 output D0, D1, D2, D3. Okay. Now when IN0 and IN1 is 0, 0, then D0 output is activated. When ion 0 0 and ion 1 is 1, then D1 output is activated. When ion 0 is 1 and ion 1 is 0, then D2 output is activated. And when ion 0 and ion 1 both are 1 1, then D3 output is activated. Okay. Now by using this truth table we draw a logical diagram. Okay, there are two input ion 0, ion 1. This is ion 0 bar, this is ion 1 bar. Okay, now D0 is activated when both the inputs are 0, 0, 0, 0. Ion 0, ion 1. D0 is ion D0 is equal to ion 0 and ion 1. This operation perform on ANDing, multiplication. So therefore here we use the AND gate. So for the output, the input of this AND gate is ion 0 bar and ion 1, ion 0 bar and ion 1 bar, because ion 0 and ion 1 is 0 0, and for 0 0 we consider a bar. Okay. Now the D1, so D1 is activated when ion 0 is 0 and ion 1 is 1. That means ion 0 bar into ion 1, ion 0 bar into ion 1. So the input of this AND gate is ion 0 bar and ion 1. Okay. Now D2 is activated when ion 0 is 1 and ion 1 is 0. That means ion 0 and bar ion 1. So ion 0 bar ion for D2. So the input of this AND gate is ion 0 and ion 1 bar, ion 1 bar. Okay. Now the D3 is activated when both the input ion 0 and ion 1 both are 1 1. That means ion 0, ion 1. So ion 0, ion 1. So the input of this AND gate is ion 0 and ion 1. Okay. So this is the 2:4 decoder. Now we write the Verilog HDL program by using a data flow modeling. Okay. Now module. This is the keyword decoder 2:4. This is the module name and this is parameter list or port list. Out ion 0, ion 1. So here ion 0 and ion 1. So first this is module, because all the programs are written in a main module function or module body. So this is module that is defined by module keyword. This is module name keyboard decoder 2:4 module name, and this is the parameter list or port list that we use to design in 2:4 decoder. Okay. Now here we declare the each and every port. Out is a output port, out is a output port, and which is, and the size of this port is 0 to 3, that means 4, because here the output are 4, D0, D1, D2, D3 output are 4. So therefore here the size of output is 0 to 3, that means 4. Input, there are ion 0 and ion 1, these two are input port. Okay. Now we write the assignment, continuous assignment statement. Okay. Now assign means what? We assign the value, we assign a particular value to this out variable. We assign a particular value to this out variable. Now this out variable has a 4 size. The size of this out variable is 4, because in 2:4 decoder there are 4 outputs. So the size of this output 0 to 3, that means 4. Now here we write the how is data flow between this logical diagram. By using this diagram we write the equation. First D0. First D0 output is activated when ion 0 and ion 1. This is the complement. This operator indicate that complement, and we use the complement for 0. We use the complement for 0. So this condition. So for D0, ion 0 and ion 1 both are 0. Ion 0, 1 and ion 1 both are 0. So therefore here we write complement ion 0 and complement ion 1, because the operation between ion bar ion 0 and bar ion 1 is a AND. So here we write the AND operation between these two inputs ion 0 and ion 1, and complement represent these inputs are 0. Complement here, the bar represent these two are 0, and here complement represent these two are 0. Okay. Now the for D2. D2 is ion 0 1 ion 1. Ion 0 and complement of ion 1. Similarly, next for D2 bar ion 0 and ion 1, and for and last is both are ion 0 and ion 1. So for D3 ion 0 and ion 1. Okay, so in this way we write the data flow modeling program. So in this for write the program by using data flow modeling, there is no need of logic gates, there is no need of knowledge of logic gate. So without using logic gate we can write the program. We just know how the data is a flow between these components. Okay, so in gate level, we saw in gate level modeling we use the logic gate, but in data flow modeling there is no need of logic gates. So designers simply know how the data is a flow between electronic component. Okay, and finally is end module, and finally is end module. Okay, now the next example is implementation of 4 to 1 multiplexer. Now in this example we will design the 4 to 1 multiplexer by using data flow modeling program. Okay, the 4:1 multiplexer. The 4:1 multiplexer means what? This multiplexer has a 4 input and 1 output. 4 input and 1 output. So for 4 input we need two select lines, S0 and S1. For 4 input we need two select lines. So multiplexer means what? There are 4 input and only 1 output. So out of this 4 input, only one output, sorry, only one input is connected to a output. This is the multiplexer. Multiplexer means what? Many into one. That means this multiplexer has many input and only one output. Now 4:1 multiplexer means what? There are 4 input and only one output. So out of this 4 input, only one input is connected to output. Now which input is connected to output? Which is decided by a select line. So by using this select line combination, we connect particular input to a output. So this is the truth table of 4:1 multiplexer. Okay. Now according to this truth table, when S1 and S0 both are 0 0, then ion 0 input is connected to output. Ion 0 input is connected to output. When S1 is 0 and S0 is 1, then ion 1 input is connected to output. When S1 is 1 and S0 is 0, then ion 2 input is connected to output. When S1 is 1 and S0 is 1, then ion 3 input is connected to output. Okay. Now by using this truth table, we draw the logical diagram. Okay. There are two inputs, two select inputs S1 and S0. S1 and S0. And this is the bar, S0 bar and S1 bar. Okay. Now this is the AND gate for first output. This is the AND gate. This is the AND gate for first input. This is AND gate for second input. This is AND gate for third input, and this is AND gate for fourth input. Now the first condition is 0 0 ion 0. 0 0, that means S0 bar S1 bar ion 0. S0 bar S1 bar ion 0. So the input of this AND gate is ion 0, then S0 bar, then S1 bar. Okay. Now the next condition is what? S1 0, S0 1. Sorry, S0 1, S1 0. Here S1 0. So here we write the bar S1. S0 1. So here S0 and ion 1. Okay. Now the input of this AND gate is ion 1, then S0, then S0 bar. So S0 bar. So for bar we connect to this line. Okay. Now the third is S1 1, S0 0. Here S1 1, S0 0. Therefore we write a bar on S0 and ion 2. Okay. Similarly, this ion 0, the input of this AND gate is ion 2, S0 bar, S1. Okay, now for IN3 both the inputs are 1 1. So S0 S1 IN3. So this input for this AND gate is IN3 S0 and S1, and finally we connect the OR gate, and this is our final output. Okay, so by using this we write 4:1 multiplexer program by using data flow modeling. So this is module Mux 4:1. This is module name, and this is the port list that we use to design the 4:1 multiplexer output. Only one output: IN0, IN1, IN2, IN3, IN3, IN0, IN1, IN2, IN3 input, and the S0 S1 select lines, S0 S1 select lines. Okay, now here we declare the port. Here we declare the type of port. So first output is the output port IN0, IN1, IN2, IN3. This is the input port IN0, IN1, IN2, IN3. This is input port, and S0 S1. S0 S1 is also a are also input ports. Okay, so here we declare module, here module name, here port list, and here we declare the type of each port. Now our continuous assignment statement. Okay, now the out, this is the output variable. So we assign the values to this variable, this output. Okay, the first is S0 here, complement S0 complement S1 complement and IN0. So 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 there is a AND operation between these three variable. Okay, so bar. So for 0 0, this is 0 0 here, 0 0. So for 0 0 we write the complement S0 complement ANDed with complement of S1 ANDed with IN0. Okay, this. Now these are connected to OR gate. That means this output, this output, this output, and this output, there are OR operation between these four output of AND gate. Okay, so because the output of all the AND gate are connected to a OR gate, so the output of this AND gate are the input of this OR gate. So there is a OR operation between these four. So first we write complement of S0, because here bar S0 and S0 and S1 have AND operation. So here we write AND operator, then bar S1. So here we write complement S1, then this is the AND operation between IN0. So and IN0. Okay, now this gate is done by using this expression. Okay, by using this expression. Okay, this gate. Now this gate is OR with this. So here we write OR. This is the OR symbol. This is the symbol for OR operation. So here we write OR. Now OR with S0, that means S0 S1 bar IN1. So how we write the equation for this? S0 and complement of S1 and IN1 here. S0 and complement of S1 and IN1. Okay, now this gate is done. Now here we again write OR sign, because the OR operation is performed between this. Okay, now the next gate, complement of S0 and S1 and IN0, complement of S0 and S1 and IN1, and then again OR sign, because OR operation is performed between these four output. And the last one is S0 ANDed with S1 ANDed with IN0, S0 and S1 and IN3. Okay, and finally end module, that means program is ended, program is done. Okay, so in this way we write the program by using data flow modeling without the help of logic gate, or without using any logic gate. Okay, it's just simply how data is a flow between electronic components. So by using this concept we use a data flow modeling for designing the any digital system. Okay, so here one more example, which is 8:1 multiplexer by using 4:1 multiplexer. So this is the diagram, and this is the logical diagram. So by using this diagram we write the program module mux 8:1. This is the parameter list, this is output parameter input here input is 0 to 7, because 8:1 multiplexer, 8:1 multiplexer means what? There are 8 input, there are 8 input and only one output, 8 input and 1 output. So for 8 input 0 to 7, these are 8 input, and select lines, 2 select lines, 0 2. Sorry, 3 select lines, 0 to 2, 3 select lines. So this is output, this is port list. Here we declare the port, and here we take two more wires, M1 and M2. So we write the equation by using this diagram. We write the equation by using this diagram. So M1 for mux 1 and M2 for mux 2. There are two mux, because we have to construct the 8 to 1 multiplexer by using 4 to 1 multiplexer. So by using 4 to 1 multiplexer, we design 8 to 1 multiplexer. So for designing 8 to 1 multiplexer, we require two 4 to 1 multiplexer. This is one 4 to 1 multiplexer, and this is second 4 to 1 multiplexer, M1 and M2. There are two 4 to 1 multiplexer, M1 and M2. So this is for first multiplexer equation, and this is for second multiplexer equation. Okay, and these equations are assigned to this output, and finally end module. So for 4 to 1 multiplexer, here multiplexer is M1, multiplexer is M1. Okay, so for this multiplexer, we write the equation M1 IN0 IN1 IN2 IN3 IN1 IN0 IN1 IN2 IN3. So for this multiplexer, IN0 IN1 IN0 IN1 IN2 IN3. Okay, IN0 IN1 IN2 and IN3, and select lines are S0 S1, 0 1, 0 and 1, 0 and 1. Here these two select lines for this multiplexer. Now the next multiplexer, which is M2, and the equation and the inputs for second multiplexer is IN4 IN5 IN6 IN7. Here M2 second multiplexer, IN4 IN5 IN6 IN7, and two select lines S0 and S1. So this is equation for first multiplexer, this is equation for second multiplexer. Now output, when complement of select 1 and M1, or with select 2 and M2. Here when this multiplexer, when S2 is 1, when S2 is 1, then this multiplexer is selected, and when S2 is 0, then this multiplexer is selected, because here we use the AND gate. So when S2 is 1, then this multiplexer, and 0, then this multiplexer is selected, and here we use AND gate. So complement of S2 and M1, complement of S2 and M1, and complement of S2 and M2, and these are the out M1. This is M1, this is M2, this is M1, and this is M2. So complement of S2, complement of S2, here complement, this is the complement of S2 M1, or with S2 M2, complement of S2 and M1, complement of, here AND gate. Sorry, this is the NOT gate. So here, suppose here is 1, then here the 0. Suppose here input is 0, then output is 1. So this is the complement of S2, and this is S2. This is S2, and this is complement of S2. So complement of S2 ANDed with M1. Okay, M1. Then S2 ANDed with M2, complement of S2, here complement of S2 ANDed with M1, complement of S2 ANDed with M1. Then complement, sorry, then S1 S2 select line S2 ANDed with this M2, this mux 2. Okay, and in between these two there are OR operations. So here we write OR operator. So in this way we design a 8:1 multiplexer by using 4:1 multiplexer, by using data flow modeling, and finally end module, and finally end module statement is written to end the module. Okay, now the next example is implementation of full adder. Then how will design full adder by using data flow modeling? This is the simple example. IN0, sorry, this is module. This is module name, module adder, and these are the port list. Sum and C out. IN0, IN1, C in. IN0, IN1, C in, sum and C out. Now here we declare the port. sum and cout. These two are the output port, and IN0, IN1, Cin, IN0, IN1, Cin. This is the input. This is the input port. Now assign cout comma sum. So here we assign the value to these two port, or these two variable, which is adder. So simply we just add this input, in0 plus in1 plus cin, in0 plus in1 plus cin. Okay, and the sum of this equation is given to sum, and carry is given to carry output, and finally end the module. Okay, so in this way we write the data flow modeling program for full adder. So in this program there is no need of logic gate. We simply apply the equation. Okay, so our data flow modeling is completed. So now in this in next lecture we will see behavior modeling. Now we will stop here.